simulated ECG signal acquisition using the Protest software. So the heart's pumping ability is dependent on electrical signals, which can be detected by clinicians through an ECG to identify different heart problems. Basically, if we want to accurately interpret the signal, it must first be filtered and amplified. So in this video, we'll demonstrate how to create a circuit that isolates ECG signals by using three basic components. And those are an instrumentation amplifier, a band-pass filter, and a notch filter, each having a specified cutoff frequencies and gain. So the first step is designing a band-pass filter. As it is known, an ECG signal is a kind of electrical signal that has a certain range of frequencies from 0.5 to 250 Hz. So we can use a band-pass filter to select only signals within this range. So how does the band-pass filter work? So in the circuit, we have chosen two resistors and two capacitors to filter out unwanted frequencies. The values are chosen so that the filter only allows signals within the desired frequency range to pass through, while also amplifying the signals by a factor of R2 divided by R1. So in this specific circuit, we have chosen R1 to be 3.18 k ohm and R2 to be 318 k ohm. So this factor becomes 100, and the gain in terms of decibels is calculated as 20 times log of V out over V in to the base 10. So if we calculate this, we get 318k divided by 3.18k, it becomes 100, and 20 times log of 100 to the base 10 becomes 40 decibels, as we can see from the AC sweep analysis. In the next step, we go to designing the notch filter. A notch filter is a type of filter that removes a specific frequency known as the center frequency. So after removing all frequencies outside the ECG signal range, we need to remove any noise that is present within that range. One of the most common types of noise in ECG signal is power line noise, which has a frequency of approximately 50 Hz up to 60 Hz. So we will use, in our country, it is 50 Hz. So we will eliminate 50 Hz frequency. So since this frequency falls within the band pass range, we can use a notch filter to eliminate it. In this case, the center frequency that needs to be removed is 1 over 4 pi resistance times capacitance. Here, the center frequency means the specific frequency or the 50 Hz that needs to be removed. As we can see from the AC sweep analysis for this specific step, there is no gain in the graph, but there is a center frequency removal which is 50 Hz from all the amplified frequencies. Step 3 is designing the instrumentation amplifier. To properly read an ECG signal, we need to amplify it after filtering out unwanted frequencies. Even though we designed the instrumentational amplifier at the third step, we will use it at the first time or at the first step when we design the overall circuit. We designed it like this way because the overall gain of the circuit is partly determined by the band-pass filter amplifier that we used in step 1. So most ECG signals have a gain at least 100 decibel. A circuit's gain is measured in decibel and is equal to 20 times the logarithm of the output voltage divided by the input voltage, as it was mentioned earlier. So we can calculate the ratio of output to input voltage in terms of resistive components by using nodal analysis. For our circuits, this leads to a new gain formula that includes components from both the band-pass filter and the amplifier. So in order to achieve a gain of 100 decibels, we need to select appropriate values for the resistor and feedback resistor components of the amplifier. In this specific circuit, we used for R to be 50k and RF to be 100. So as a whole, we will get a factor of 500. As it can be seen from the AC sweep, we have got around 60 decibels gain, since based on the calculation, we will get around that value when we finish the calculation, which was gain in decibels. We have now reached the step at which we test the components. Each component in the circuit was individually tested using the Proteus AC sweep octave analysis tool. We set the parameters to 100 points per octave, starting from a frequency of 0.01 Hz and ending at 100 kHz. We used input voltage of amplitude 1 volt, but this value can be adjusted as needed. The most important aspect of the AC sweep analysis is to observe the shape of the output signals as the frequency changes. Now that we have designed all the components separately, it is time to put them all together. Usually, amplification is done before filtration. So, as I mentioned earlier, the instrumentation amplifier was placed at the beginning. The bandpass filter amplifies the signal further, so it was placed second, before the noise filter, which only filters out specific frequency. The entire circuit was also tested using an AC sweep simulation, which produced expected outcomes, including amplification within the range of 0.5 up to 250 Hz, except for the 50 Hz notch range, which was filtered out as intended. Our last step involves inputting and testing all signals. So the process involves taking a noise enhanced .wav file from an audio streaming tube and loading it into the Proteus simulation software. And here, in order to see the oscillation, we connected an oscillator to the whole circuit, and as it's expected, an ECG signal appeared. Despite the distorted and noise-enhanced nature of the source file, it was still possible to extract the characteristic P-wave, QRS complex, and T-wave of the ECG signal, which is a significant achievement. The next step would be to pass a clean ECG signal through the filter to see how accurately it can be filtered. Here we didn't find any clean ECG, so as it can be seen from the circuit and the oscillator, we have got a P wave, which is like a little notch, and a QRS complex that is high in amplitude, and the next is the T wave. And we finish our project by this. Thank you very much.